Yeah, so thank you for the introduction. My name is Abril Guzman, and yeah, I'm coming from NFDI-MatWerk. I work in Forschungszentrum Jülich, actually, in the Institute for Materials Data Science and Informatics. And I want to talk today a bit about the work that we have done on ontology development for material science and also trying to achieve semantic interoperability. So I'll start with a bit of context and the NFDI-MatWerk vision. So NFDI-MatWerk is the consortia for material science and engineering. And the idea that we have, so we like to show this schematic representation of our vision, which is to have a decentralized infrastructure, but through building a knowledge graph of all of the metadata and all of the resources that are out there in the community, then we can achieve the harmonization and interoperability. So we see here the different aspects where we work. So we have structure, documentation of simulations, but also of experiments. And a big topic in the MSc community is the data reuse across different scales. So we have, of course, atomistics, but then we want to go to continuum and other methods and so on. On the other hand, then we have the integration of heterogeneous sources, the findability and accessibility of federated resources, and exchange with other knowledge systems. So this is a bit more on the information technology level. So the question is, where and why do we need ontologies in this vision? And of course, that comes to the verification of research data, which I'm sure everybody knows, because the FAIR principles ensure interoperability and reusability. So that's the I and the R. So we need, if we have some data, there are many questions that will come up, right? Like how the data is organized, what are the concepts in it, unit dimensions, provenance, and some administrative aspects. So the idea is that all of these, the answers to all of these questions belong in a formalized controlled vocabulary. And that's then where the ontology development comes in. So I will not go in detail about the different ontology theory and so on, but I just want to give a few pointers so that we're all on the same page. So we can define an ontology as a formalization of classes and concepts and also their relationships. And the idea is that it allows for interoperability and standardization. So different communities can come and define what they mean by certain words. And then by using unique identifiers for all of these metadata fields and the things that are in the ontology, then we can comply with FAIR and have FAIR metadata. So we have here an example of a schematic knowledge graph. And this is also the other benefit of building ontologies, that we can instantiate and create knowledge systems. So we have triples, and all of the data then is connected in a graph. And in material science specifically, we have highly interconnected data. So this is beneficial in that way, so that we can set up structured data in a way that is also extensible, depending on what we're doing. So here we can see that the difference between any knowledge base and a knowledge graph is that we have the backbone of an ontology. So in this example, we have a steel ontology and a chemistry ontology. So here is the benefit that we can have different communities defining different aspects, and we can put it all together in a knowledge graph. And these can be used to infer new information for reasoning purposes. So the idea is that we can have AI-ready data. So we do this in the task area ontologies for material science. So yeah, this is the people. And we have two co-speakers. So Stefan Samfel, in the, where I come from, in the Institute in Jülich, and from the material science part, and also Professor Harald Sack from Fisker from the computer science and the information service engineering. So so when we talk about ontologies, we have different levels of abstraction, and this is where the work goes in. So we start with a top-level alignment, then we go down to the mid-level. So we have lateral harmonization, the bridging of different domains. And as we get more specifics, we go to the domain level. So we are organizing knowledge about specific methods and data within a domain. And then if we go further down, so more specific, we have the application level. So describing a specific data set or process. And this is usually then where the scientists are interested because they want to have the specific details of their data set and the data that they are producing, right? But the top level and the mid-level alignment is also important because we also want to reach interoperability within different domains and with other NFDIs and so on. So this is an overview and non-exhaustive overview of the different ontologies that are being developed and used within NFDI-MatWerk. And they are on the different levels. So we have the top level, so usually is a decision in material science if you align to BFO, the basic formal ontology, or to EMO. And of course, we don't redefine everything from ourselves. We are also using external vocabularies. So these are the ones marked in gray here. For example, materials design ontology, which is based on Optimate, the EM glossary from the Helmholtz metadata collaboration, and maybe the platform Material Digital, PMD core, and so on. So this is the way then that we can reach interoperability and connect with other consortia and other initiatives. So this is the outline. I want to show you 3 specific examples. And we start with the top level and mid-level alignment, so the description of resources in NFDI. So for this purpose, we developed the MatWerk ontology. So our first release last year focused on representing the different resources of all of the groups within the consortia. So this is, community structure, so researchers, affiliation, administrative metadata. Then we had the infrastructure, so different software, ontologies, schemas, also instruments and facilities. So whatever people have, there are resources that they use for their research. And finally, data, repositories, databases, published data sets, and reference data. So this ontology is available here, and the idea is that it was developed as a part of the NFDI ontologies. So there is an NFDI core, and the idea is that different consortia, which agreed then to align to this standard, develop different modules according to their specific requirements. So we have here MatWerk, NFDI for culture, for data science, and then further extensions in for memory and MARDI are planned. And then the idea is that all of these consortia build knowledge graphs of their research data and their resources, and this can be interoperable. So we can allow for federated querying among all of the data infrastructure in Germany. The current status is that we this year released version 2, where we try then to have all of the previous representation and also bring it closer to the MSc domain. So then starting to add specific data and metadata about the material science. So we have some lightweight material descriptions, so something like type, properties, conditions, and we have a controlled vocabulary of all of the different properties of the materials. And this is not very semantically rigid, so it's very lightweight in a way that we can provide easy metadata templates to the people who belong in the consortia, and they can fill it up, and that's kind of the easiest light way of achieving some harmonization. But of course, when we, and then there is also the computational workflow and experimental workflow that is always very important to the people and to describe what they are doing. Of course, when we talk to people, then they say, well, my material is not only this is not enough. They really want a detail of what is inside the material, specifically microstructure and what the material is. And in this, that motivated us to develop crystallographic defect ontologies. So this is going more towards then the description of what is exactly inside the material. So as you know, crystal defects is a big topic in material science and engineering. So a lot of the studies and a lot of the papers out there are focused on this topic. And we can see here that, most of it is engineering, but there is also from chemistry and from physics. So we have already a multidisciplinary data. And if we see this schematic here of the different defects, we see that it goes across different scales. So we can have something like point defects on the atomic level, but then we can go up and have plane defect, grain distribution, cracks, and even go up to 3D bulk defects. So that brings another source of heterogeneity, so this multiscale aspect of the material. And of course, then we have the usual experiment versus simulation and the interoperability between these two types of data. So this is all to say that we have a lot of data heterogeneity, which is perfect then for the application and defining ontologies that allow harmonization. So for this, we developed the open crystallographic defect ontologies. So this is openly available in a GitHub organization, and we try to follow a modular approach. So we have point defects, line defect, and plane defect ontologies, and we try to work then with the community and extend it according to the research questions. Of course, we align to existing ontologies, so MO, MDO, QUDT for the units, and we sort of try to take care of that. And yeah, these are OWL implementations, so we're using OWL to define all of these things. So as I said, we have different participant projects from different institutes. So we have some stacking fault work, some about fair grain boundaries, hydrogen microstructure interaction, and then the application in atomistic simulation. So this is the next point that I want to show you. So really, the infrastructure use case in the atomistic simulation field. So this is what you saw before, right? This schematic representation. And at the moment, the way that the defect ontologies are defined is mostly focused on the atomic level. So of course, as you go up the scale, then you have distributions of defects and more statistics about it. And this is something that we have not yet included. So it's mostly about the atomic level description. And then here we have added then the material simulation. So we have developed two ontologies to describe the crystallographic defects in the, from the modeling perspective. So I just wanted to say a quick word here about the computational material science struggle with reproducibility. So of course there is a lot of effort and is actually way ahead, I think, of the experimental partners. But this year, in the beginning of the year, Aaron Walsh wrote this paper about open computational material science, where he says, even something as seemingly straightforward as the calculation of a point defect in a crystal requires combination of dozens of files and several codes. So this was our motivation then to try to add more concepts and physical meaning into then the input structure and the way that our data is organized. So if I show you a ZIP file or a postcard file, and I ask you if there is a grain boundary plane, then you don't know that, right? And that's what we want to use the ontologies for. So the aim is to establish semantic standards for representing material structures, especially the defect structures, simulation workflows, and calculated properties. So these are the three areas that we focus on, and build knowledge graphs that include structure-property relationships. So that's what we want to reach. The way that we did this at the application level is, of course, going to the software that is used in the community. So we try to reach agreement through code compatibility. So we look at different software packages and how they organize their data, how they call their variable, and then try to use this as input for the ontology development. On the other hand, we also have a lot of data resources in the field. As I said, there is a lot of progress, and in there is Nomad, Materials Project, and so on. And then we also want to be interoperable with all of the different platforms out there. So this is the Computational Materials Sample Ontology. So it's describing the structure. And I will not go into detail of all the different concepts. It's just to show you then that we have not key value pairs, but we have then this connectivity and the relationships between all of the different concepts. And these are the different software that we are supporting at the moment. So these are mostly post-processing or processing Python tools, and also the input files for structure, the packages that create defect structure like HGB, AtomMan, and so on. And then here is where we want to extend to Nomad and hopefully find some synergies there and use the terminology that we are developing in Nomad. So at the moment, this is very early. So we started with our Nomad Oasis, and that's the status of it, and we want to prototype there and see what is the best way to do this in the future. So similarly, we have atomistic simulation methods ontology, where we use Provo. So this is the provenance ontology, to have then the definition of the provenance and the connection between all of the different workflows. And we are at the moment supporting Pyro and atomistics, but also VAS, quantum espresso lamps. And yeah, we are, as we go, try to support more and more software. So the ontologies are available here. They're also open in the GitHub organization, and so the documentation and so on. So once we develop these ontologies and we say, OK, so what do we do with it? How do we use it? And this is where we wanted to create knowledge graphs. So we collaborate with the task area workflows and software development, also in MatWerk. So this is Tilman Haeckel and Sharath Menon from BAM and MPIE. Well, the Max Planck Institute for Sustainable Materials now. And they are part of the Pyron team. And we developed this tool called atomRDF, which uses the ontology to represent the atomic structures and workflows. And this is installable through pip and conda, is openly available as well. So the gist of it is that we have data generation tools and publish data. And we take the ontologies that we define in the software, and then the software creates a knowledge graph without the user having to know semantic web technology, Sparkle querying, and so on. So all of that is done by the software automatically, and then we can create a knowledge graph. So for example, this is a visualization of DC3 data sets, which is around 2,400 atomic configurations from molecular dynamics. So this is how it would work. We have here a piece of code which is just running a minimization using Pyron and lamps. And in the backend, then this data, the knowledge graph is organized and created according to the ontology, which then will make it completely semantic, interoperable, and fair. So yeah, that brings me close to the end. An outlook of where we want to go with this and the next steps. Well, first, we want to go up the scales. So we want to then define things and also do the material simulation for higher scales, so multiscale modeling and so on. But also, we want to add materials characterization aspects. So here, for example, with the EM glossary, or maybe with the Nexus, with Markus Kubach, then we are thinking of doing something that also includes the experimental partners, and yeah, so that we can have this duality of the simulation and the experiments. So that brings me to the end. Hope I was able to show some of our work on ontologies for defects and simulation, which are being developed with specific research questions in mind. And we also are working on the creation of application-level knowledge graphs of simulation data and the integration with workflow environments. I'll be happy to take any questions.